All right. This time we're going to take a look at the bullet being fired from a rifle problem. All right. It says a 10-gram bullet is fired horizontally from a rifle with a barrel that's 85 centimeters long. They want us to do LOL diagrams for some positions there. And then the question they're going to ask us to solve is, assuming the force exerted on the bullet by the expanding gases in the rifle is a constant 5,500 newtons, what speed would the bullet reach at the end of the barrel? So what's that muzzle velocity as it exits the muzzle of the gun? Okay, so there we go. So quick sketch. Right? Always going to start sketching the problem. I'm going to say, here is that barrel of the gun, right? And let's move our stock and some kind of like hammer and slide or whatever. Trigger. There we go. All right, good enough. And so that bullet is going to start here. It's going to get triggered. It's going to go right out the gun. We're analyzing it going from here, 85 centimeters down to here as it exits the gun. All right. Let's see here. They told us that this is 85 centimeters. I'm going to immediately change that to 0.85 meters. Okay, so we want to use a metric system. The base unit for length is meter. And what else do we know? They told us it's a 10-gram bullet. And so you say, well, 10 grams, we want to convert that to kilograms. That's the base unit we always use in physics. It's kilogram. Metric system, actually. And so if I go ahead and I take 10 grams and then convert it to kilograms, I'm going to divide by 1,000 for kilo. So I'm going to decimal point 3 places left. 0.01 kilograms is our mass. Right? We're trying to find the speed at the end, the muzzle velocity here. And let's see here. They say we're going to assume that as that bullet is traveling along, so kind of while it's traveling along there, those expanding gases behind it are pushing it with an average force of 5,500 newtons. Right? So there's my sketch. Okay, let's go to the LOL diagrams. They want us to do an LOL diagrams for what positions? They say bullet and gun at rest, the instant the bullet exits the barrel, and the instant before the barrel strikes, the bullet strikes the ground. Okay, all right. Well, I guess I'm going to have to say after it leaves the barrel, it's going to start dropping immediately, right? And it'll hit the ground out here somewhere. All right. So they also want us also to take a look at the spot just before it hits the ground. Okay. So here we go. LOL. Let's call these. We're going to call these positions A, B, and C. Here we go. Junk, 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 junk. Right? Okay. So our LOL diagrams. Position A, position B, energies at position C. And here's our transfers between. Okay. We got to set up our system, right? Our system, certainly we're going to look at the bullet. Do we want to include anything else in our system besides just the bullet? You say, well, what are our options? Well, we got to think about what other forces are acting on it, right? You say, well, I suppose as it slides along in the barrel, would you be upset if I did my force diagram on top of the sketch? I think you'll be okay. There'd be a gravitational force. There'd be a normal force. Would there be like some sort of a frictional force with the barrel as it slides along? Probably. We're going to go ahead and we're going to have to ignore that, frankly, in this problem. They didn't give us any information about it. I'm going to assume that friction is a lot smaller than 5,500 newtons. I'm going to assume it's small enough to ignore. We're going to assume that friction force is negligible. Is that a good assumption? Well, we're kind of stuck with it. But we're going to have to do that. So we're going to kind of ignore the friction force here. They didn't give us information about it to solve. Sorry. If you want, you can think of this 5,500 newtons as the combined forces on the bullet while it's in the barrel, maybe. Anyway, Once it leaves, you know the only force on that bullet while it's traveling along here, right? It's just going to be gravity. Not the only force. Ignoring air resistance here. So here we go. Assuming we're ignoring that. Think of this. So what else acted on the bullet? The barrel did, and the expanding gases did, and the earth did. Those are the three things pulling on it. Do we want to include the gases? No, because we're going to do a work calculation with this force. We have no we have no other. So we're not going to include it. We're going to make that a force from outside the system. They've given us that force. We're going to use that. So I don't want to include the gas in the system because we're going to have a work term. The barrel, you say, well, this force is perpendicular to the motion. It's not going to be doing any work anyway. It's not going to be changing the energy of the system. We probably don't need to include that. We're ignoring the friction with the barrel. So I'm probably not going to want to include that. Then the earth, you say, well, that gravitational force isn't going to do any work here because it's perpendicular to the motion. But here, it's going to start pulling in. It's going to start to have a vertical motion. It's going to be doing some work along the path here, a better way of looking at it, as we go. So I am going to have, if I want to, I could include the Earth in the system, and then I'd have a gravitational potential energy term. Or I could leave the Earth out of the system, and then I would have a force doing work while we're moving from B to C. They're not actually going to make me calculate anything for out here. The only calculation they're asking for is for the muzzle velocity here. We're going to go from here to here. So it doesn't actually really matter whether I include it or not. As long as I realize gravity's not doing any work from here to here. So, I mean, in general, it doesn't hurt to expand the system. I'm going to go ahead and put the Earth in, but it'll make a little change in how things go here if I include the Earth. All right, so here we go. Let's just do it this way. Okay, let's talk now. Next, I would go for what is there energy being transferred in or out of the system? And you say, well, as I go from A to B, from here to here, there is an external force acting that's going to do work, and that's the force from the gas pushing in the direction of motion. So this is going to be putting energy into the system, making the bullet go faster and faster. So I'm going to draw my arrow going into the system. This is work done by that expanding gas. All right. Now, we are going to be able to calculate that work, all right, and get a precise value. But my LOL diagram is not meant to be the big end result, is to do a super accurate LOL diagram. My goal here is the LOL diagram to just be helpful for me in setting up my equations, for seeing what's happening in the problem, getting a grip on it. So I'm not going to bother calculating out so I can make a super accurate one. I'm just going to pick a value. Hey, look, it put 10 units of energy in. There, I just picked a value. I know, you're disappointed. I usually use 12. All right, fine. There's 12 units of energy in. All right, at the start, so now you say, okay, what about from B to C? Are there any outside forces doing work? You say, well, those expanding gases behind the bullet, they're not going to be pushing on it anymore now that we've left the barrel. The gravitational force, well, that's between the Earth and the bullet. We made the Earth part of our system, so I won't have any energy transfer going on between B and C. So that's done. So that's the energy transfer diagram's done. Again, if I had chosen to make the Earth not part of the system, then I would have a work term here of energy going into the system for work done by gravity if I didn't include the Earth in the system. Because the gravitational force is helping it to speed up vertically, right, as it falls. Okay, moving onward. Gravity has a component of the force along the motion. Okay, going to, next we figure out which energy types are we going to include. So I kind of run through my checklist. I only have to include energy types if they're changing. So first, kinetic energy, is it changing? You say, yeah, the speed, we're starting from rest here. My speed at A is 0 for the bullet. And then we're going to find the muzzle velocity here. We're changing speeds. So kinetic energy is something that we will analyze. Gravitational potential energy. You say, are we changing heights? Yes, and I include the Earth so I can have UG. I'm not changing height from A to B, but we are changing heights from B to C. So I'm going to include UG. Let's see here. Elastic, do we have anything stretchy that's being compressed or stretched? You're like, well, what if the gas is being compressed and stuff? It's going to end up back, That's going to end up being resolved by the end. We're not going to worry about it. We'll be back where we started. And then you say, what about, chemical? Do we have a chemical reaction? You see, there's a chemical reaction, and now I'm going to make a distinction, okay? This thing that you load in a gun and you fire, the little bit that goes flying out is the bullet. The whole thing you put in is called a cartridge, and it's got this part behind the bullet that's like full, like the, your gunpowder and stuff, right? Does that make sense? And like the casing, right? That stuff doesn't go flying out the end of the barrel. It's just the bullet that flies out. Okay, so I'm not including that gunpowder in my system here. So I don't have a chemical reaction going on in the bullet itself. Is what I'm saying. So there's no chemical potential energy change to worry about. Okay, if you wanted to include the cartridge as part of your system and all the gunpowder in the back, this would look different. Okay, but I'm going to do it not including that. But if I did that, then those expanding gases from the chemical reaction, that would now be something inside the system. It wouldn't be an outside force. See what I'm saying? So I really want to make my system be just that bullet that's coming out. It's just that the actual projectile. Okay, so moving onward. So I don't have that. Do I have thermal? And you say, well, yeah, that chemical reaction is going to heat up the barrel and stuff, but the barrel's not part of my system. It's going to heat up the bullet. Yeah, a little bit. It's not a whole lot of energy involved in that. I'm going to neglect that, I think. So like thermal generally comes from like friction and collisions, and they didn't give us really any data to work on to figure out that friction energy. So I'm kind of stuck. I'm just not going to include it, right? So I'm not going to include the thermal. Much of that is going to be used to heat up the barrel of the gun and heat up the air, and that's not part of my system. It's coming from energy that was in the chemical compounds and the gunpowder in back, which again is not part of my system. So I'm not going to worry about the thermal. So this is it. That's what I'm looking at for my setup. So do we know any of these that are zero? You say, well, kinetic energy, speed was 0 at the start, so this here is going to be at 0. But I'm moving at the end of the barrel. In fact, we're going to try to find the speed as we exit at. And we're moving as we hit the ground, so those aren't 0. Gravitational potential energy, that depends where I choose to call height 0. Most of us like to call the lowest height in a problem 0. If I did that, then maybe I would make the height of the ground here. That's the height at position C. See, the height at C is 0. If I do that, that makes my UG at C 0. But I'd have some potential energy here. Now, they didn't give us any data on how high we're firing this from. I'm just going to say, I can't imagine that potential energy from that height. That'd be kind of like the kinetic energy you get if you dropped it from that height. If I'm firing from normal height here, that's not much energy compared to like the energy from it being fired out. So I'm going to say that that is some tiny little amount. In fact, I'm going to say it's 1 unit of energy. Right? Now, so this is my starting energy of the system is 1 unit. Going from A to B, I can see that 12 more units of energy went into the bullet for the system. So now we have 13 units. Is the gravitational potential energy going to change from here to here? No, we're at the same height at A and B. So this stays as 1, but we've gained 12 units. Where's the 12 units? It's in the kinetic energy. Now we're going to go from B to C. You see, from B to C, our gravitational potential energy is 0. Now, going from B to C, did energy enter or leave the system? No. The total energy is 13. Total energy here has to still be 13. I've got nothing in gravitational. All 13 must be in kinetic. All right, so that's what my energy bar graphs would look like. Okay, so that's the end of part A. Part B of the problem says, can we find the speed of the bullet at the end of the barrel, that muzzle velocity? So I'm going to do my energy calculation going from the other spot where I have information from A to B. And we know the force that acted from A to B. Makes sense to make A and B our start and end point. So here we go. We're going to go from A to B, right? And again, our system is the bullet and earth. So when I set up my equation, sigma W is delta K. I also can do delta UG if I want, because I'm including the earth. However, I noticed that in going from A to B, there is no change in the gravitational potential energy. So the delta UG is just going to be 0. So, because we're not changing height. Outside forces here doing work. Is the normal force going to do work? No, because it's perpendicular to the motion. Is the gravitational force going to do work between A and B? No, it's perpendicular to the motion. I just have work done by the gas. Delta K, that would be the K final minus the K initial, my kinetic energy at B minus my kinetic energy at A. And you say, but the kinetic energy at A, there the speed is 0, so that's going to be 0. So that's going to drop out. So I end up with this equation with just these two terms. There is my work energy theorem showing only the non-zero terms that I was asked for. Okay, we were trying to find the speed. That's going to be in the kinetic energy equation. Awesome. Doing my calculation. Work done by gas. I'll use the work equation. The force dotted with the distance, which means I got to multiply by the cosine of the angle between them. What's the angle between the force of the gas and the direction of motion? Well, they're going the same way down the barrel. It's a cosine of 0 degrees. They're going the same direction. Angle between them is 0. And then the distance we go is that 0.85 meters. I don't know why I just put the value in there. Let's just call this delta x, sorry. Delta x, I don't like to put my numbers in quite yet. And then kinetic energy, we have a formula that's 1/2 the mass times the speed squared. Okay, there we go. We are trying to solve for that speed. Do we know the mass of the bullet? Yeah, we do. Do we know the distance it's going to travel, get pushed through? Yes, we do. Do we know the force of the gas? Yes, we do. We have everything we need to know to solve this. I could rearrange it and say 2 over m. So I've got 2, force of the gas over the mass. Cosine of 0 is just 1 times delta x. Plug my values in. It'll be 2 times 5,500. Yeah. Times that 0.85 meters divided by the mass, which is 0.01. Okay. Punch that in my calculator. Oh, I need to take square root, don't I? So it's b squared in the equation. Okay, punch that in my calculator and see what we get. 2 times 5,500 times 0.85 divided by 0.01. Take a square root of that. I get 966.95 meters per second. We're going to we're going to make that 966.95. You know what? That'll round to a nice 997 meters per second. 6.9. Okay, so there we go. And that is that problem. As a side note, this speed is honking fast. A lot of guns will fire bullets that are supersonic, that are faster than the speed of sound. The speed of sound, I want to say it's around 240 meters per second. So this thing is like, doing over Mach 3. That seems unlikely. I probably ought to adjust the numbers in this problem to make it a little more realistic. But yeah, so that you get a reasonable answer at the end. But that's it. Okay, unless I made a mistake in my calculation somewhere. I don't think so. I think we're all good. Okay.